present for 4.di.1. Distillation columns. Woo! Alright, so we have this system here and we were asked to do a lot of things, so bear with me, we're going to try and go through this and get everything done. Alright, so first thing we have to do, how many stages does our distillation column have and what is the feed stage? So we have this. Let's go ahead and count off stages. So I got 12 stages with feed stage of 6. How does that look? Yeah, well.
You need to do the other way.
What do you mean I have to do the other way? What other way?
You need to count them off of the curvy line.
The curvy line. What's the curvy line called? The equilibrium line. What am I currently counting them off of? Operating line. Yeah, so that's actually not a good idea. I want to count them off the equilibrium line. Thank you, Will. Alright, good. So now I'm counting them off the equilibrium line. My feed stage, my crossover point here, so my feed stage is 5. Does that make sense to everyone? Alright, cool. Next thing we have to do. What is L over V in the stripping section and what is L over V in the rectifying section? And what is the temperature in the cooler? Alright, so L over V is basically the slope of each of these sections, correct? So I can calculate the slope. Which section is this? It says on the top of my slide, for those of you wondering. The stripping section. And what's this section? Alright, good. So now I get the slope of my rectifying section. So 1.29, I just use the 2 points here. Remember, picking my points that are farther apart is better than picking ones that are close together. More error caused if I pick this point and calculate the slope. And if I pick this one and that one, right? Okay. Got my slope for that. Then I did my rectifying section up here. Got my other slope. Alright. What is the temperature of the cooler going into my system? What's the first thing we need to look at to know the temperature of that on this diagram? Yeah? The temperature of the feed what? Or the compositions of the feed what? The feed stage. So this is my feed stage. So where am I supposed to be looking at here? The point on the equilibrium line. Right. So it specifies here that the feed enters as a liquid vapor mixture with the same composition as the feed stage. So the composition of my feed stage is the composition on the equilibrium line. So right here is where my compositions are. So I can just read those off, and I can get my feed composition of 0.37 and 0.59. So what do I do once I have these two numbers? How is that going to tell me the temperature of the cooler? Yeah?
Are you find it on temperature map?
Yeah, so I need to switch over, go onto here, plot those out, and I have my temperature tie line, which tells me that the temperature of the cooler is about 79 degrees Celsius, okay? Does that make sense to everyone, how we did that? Awesome. Okay, the next thing that we need to do, part C. What is the flow rate of the product? Flow rate in the condenser. Now, where's my product stream? Alright, flow rate in the product stream. Good. So, what did you guys do to get the flow rate in your product stream? Yeah, Dan.
Mass balance.
Mass balance over the whole system, kind of like my one right here. Cool. Alright, and what did you guys know, what did you know about the system?
So basically, if we're going to assume the purge negligible since it's like 1,000% or whatever.
Yep, we're going
just going to model it where what comes in is that one series coming out the other series just
Okay, so I have a question for you guys. How come you can do that? I thought moles weren't conserved. How come I can just say that the mole's in is the mole's out? Brittany?
Because the chemical reaction is states that the moles are conserved.
Correct, because my moles are conserved in my chemical reaction. So 1 mole of E is going to make 1 mole of M. So my mass balance becomes a mole balance. And I know that 1 mole of E in equals 1 mole of E out. So there must be 52 mole percent of E out. Alright. So now let's do the flow rate of my condenser, okay? So, I'm doing the flow rate of the condenser. The first thing that I did is I wanted to make an equation for a mass balance or a mole balance around my condenser. It's basically, I know this vapor stream coming in, I know my product stream coming out, and I also have this liquid that's going back into stage 8. So I have V equals L plus 52. So that's all good and dandy, but how do I know the relationship between my liquid and my vapor? Yeah, Rachel.
You know that L over V for that section?
Mm-hmm.
So you can set your slope equal to V minus 52 over V.
So I know my L over V for this section. So which section is it? Remember, I had two L over V's, so how do I know which one it is?
The right side.
Yeah, it's my top. So it's 0.79. So I can go ahead and plug that in, and I'm going to get a V of around 240 moles per minute going in. Okay? Does that make sense to everyone? Any questions about that? Yeah, he's cute. I know. All right. So, part E is telling me that my reactor output changes. So I'm only going to get 40 mole percent coming out of my reactor. Okay? So I've gone ahead and marked 40 mole percent on the graph here for you. So I want to know, are there any operating parameters that I need to change? And how are you going to know that? What did you guys do when you were looking at this problem? Anyone? You're looking at this problem and you're like, wow, what's a useful graph maybe to go from this? Maybe I want to go to my temperature map. So earlier I found out that I had I knew where my two sides were for my equilibrium stage, right? We took my equilibrium stage point off of here and we put it on my temperature XY graph. And what we can say is that 40% is still within the range. Another way to look at that is by, we've been talking about how if I have 40 mole percent here, that my equilibrium stage can touch between 40 horizontal and 40 vertical and 40 horizontal. So my feed stage touches still within that range, which is mirrored by the fact that 40 is within this line. So basically, my stream is going to break into the same liquid and vapor compositions as it did before at 70 degrees Celsius. So I don't have to change my operation. Pretty cool. All right. So now I changed it to 30. What if we approach this the same way? How did you guys do this? What did you guys get? Can you get this far? Yeah.
When you go back to your temperature diagram, you realize it's now within.
Yeah, so I can go back to my temperature diagram, and 30 is no longer within my range. If I heat my stuff up to 30 degrees, it's still all going to be liquid, right? So there's no liquid vapor composition, so I need to change my feed point. So my constraint is that I want to keep my column the same. So I want it still to feed into the fifth stage like it did before, and I still want we have to fit into a tie line on my t equals xy diagram that includes 30%, and my outputs still have to be the same, right? So what is the only thing I can actually change about this process then? I say technique, guess and check. What are we guessing and checking to do this? Yeah, Dan?
Different temperatures of the cooler.
Different temperatures of the cooler. But if I guess and check temperatures of the cooler, what's that going to tell me?
Compositions of the liquid and vapor going in.
So it's composition of my liquid and vapor in my feed stage. So it's basically going to change my equilibrium point for my feed stage, right?
Yeah.
But can I just change the equilibrium point of my feed stage by itself? Isn't that going to affect the rest of my column? Yes. So what do I have to change about my column? Yeah.
How many levels you add on top?
How many levels I have on top. But if I change how many levels I have on my top, then I'm changing the feed stage, aren't I? That's the same thing. If I change my feed stage, it's changing how many levels I have on top. Yeah, Jess?
The slopes of the operating.
The slopes of my operating lines. What I'm going to change here is the slopes of my operating lines. So I'm going to take my compositions and I'm going to draw myself some new operating lines. And this is the part where the guess and check comes in. How steep do the operating lines have to be? Then I'm going to go ahead and draw my stages. So now I'm within this 30 degree, or 0.3, but my feed stage is still feed stage 5. Okay? So, does that make sense? I'm here. My feed stage is this stage 5 still, and it's within my 0.3 and within my 0.3. Okay? So, that tells me that I have to change these. So how do I find the new temperature of my cooler? Same way as before? Yeah, Brittany?
Okay, you take the feed stage and then use the temperature composition graph to figure out the temperature of the coolant.
Yeah, so I grab those off of my equilibrium graph again. My new feed is this. I can plot that on there. And as expected, 0.3 falls within my range, okay? So that's good. You know that's working. All right. So, also I can check my LV stripping and my LV rectifying in the same way, just get the slopes of those. That's going to tell you your two reflux ratios. All right. So finally, part G asks, what is the minimum amount of M in the reactor output that can be fed into the distillation column and still provide some product with 98 mole %? So how did you guys go about finding the minimum amount of N? What do I want to do? So I know I want to get to 98 mole %. So if I'm operating at a minimum, basically, when someone says to me like, oh, I can do a minimum or I can do a maximum, that means that I can do things kind of crazy, right? I can do things so that it doesn't actually, like, it wouldn't really work. Meaning that I'm going to make my operating line my total reflux line. I'm going to make it y = 1. So basically, everything that's coming out, I'm sending back in. I'm not getting anything out of that column. So let's just start up there and go all the way down. And I can see how far I get to 5 stages, because that was our parameter on this column, is that we're feeding into each 5. So it doesn't matter how many I go down here below 5. It only matters when I get to 5. So I can find that composition at the bottom of 5, and so my feed, the lowest feed I can have, is at the equilibrium of my stage 5 at total reflux, which is given right there. Does that make sense? Yeah.
If you need to provide product and your operating line is on the XY line, aren't you getting no output?
Right. So this is an idealized case. We're not actually getting anything out, right? So what we would have to do is we'd have to move infinitesimally a little bit up from this. So we would move up just a little bit to make it so we were getting some off. But this is just asking for the minimum, and that's why you know that you can do something like this, because it's not asking for like, oh, how much are you getting out? It's asking for the minimum amount possible to get out the top. But you're correct. In this, we wouldn't be getting anything out of our top, okay? Okay? Any other questions? We're all set? So you can go ahead and put that on your X and Y diagram. It tells you your temperature and your overall composition is about 7%. Okay? Good? All right. All done. Good job.